Every 3 hours, your wallet service crashes with an OOM-Kill. The heap dump shows millions of transaction objects. The root cause? Your balance cache loads every single transaction for an account just to compute the balance. For power users with 100K transactions, that's a memory bomb. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover design a digital wallet. In this lesson, you'll learn how to design a digital wallet that prevents double spend, survives crashes, and scales to millions of users. We'll cover the ledger-first pattern, idempotency keys, optimistic locking, sharding, and the reconciler pattern. A digital wallet system manages user balances and processes transactions. It must ensure every transaction is atomic, durable, and idempotent. Think of it like a bank teller's drawer. Every deposit or withdrawal is logged before the cash count is updated. The single biggest mistake is treating a balance as a mutable field. Instead, use an append-only ledger. Every transaction is a row in a transactions table. The balance is a derived value, but for performance, you cache it with a write-through pattern. Here's the atomic transaction. First insert into the ledger, then update the balance with a check to prevent overdraft and an optimistic lock on the version column. If the update affects 0 rows, the transaction rolls back. Networks fail and clients retry. Idempotency keys ensure that processing the same request twice produces the same result. The client sends a unique key, and the server deduplicates using a unique constraint. This middleware checks if the idempotency key already exists. If so, it returns the cached result. Otherwise, it inserts the key with status processing and proceeds. Duplicate inserts fail on the unique constraint. Never let the client generate the idempotency key. They might reuse keys across different transactions. Generate it server-side from a unique request fingerprint, or require a UUID that you validate is unique per account. Optimistic locking beats pessimistic locking for high concurrency. You read the current version, compute the new balance, and update with where version equals old version. If another transaction committed first, your update affects 0 rows and you retry. This sequel reads the current state, then attempts an update with the same version. If no concurrent update happened, 1 row is affected. If another transaction committed first, 0 rows are affected and you retry. Using Select for Update on a popular account causes queuing and timeouts. Optimistic locking avoids this. If you must use pessimistic locking, keep the transaction short and consider sharding the account into sub-accounts. When you have millions of accounts, shard by accounted. All transactions for an account go to the same shard, keeping the ledger and balance local. For cross-shard transfers, use a saga pattern with compensating transactions. This pseudocode routes transfers to the correct shard. Single shard transfers use a local transaction. Cross-shard transfers use a saga pattern with compensating transactions to maintain consistency. No matter how careful you are, transactions will get stuck in pending state. A reconciler background job scans for pending transactions older than a threshold and either completes or reverses them. It must be idempotent to avoid double processing. This reconciler finds pending transactions older than 60 seconds, checks the current balance, and decides whether the transaction was already applied. If not, it attempts to apply it with an optimistic lock. If your reconciler runs concurrently with the main transaction handler, you can get race conditions. Use a distributed lock on the transaction ID or a status field with atomic compare and swap to claim ownership. This is the same issue we highlighted at the start. Here's exactly why that happened. The balance cache was loading all transactions for an account into memory to compute the balance on every read. For power users with 100K plus transactions, this blew the heap. No pagination, no streaming. The fix was to add a materialized balance column updated atomically with each transaction. Now the cache stores only the balance, not the transaction list. Balance computation uses select some amount with an index for occasional audits. Never load the full ledger into memory to compute a balance. Store a running total and update it atomically. This is the exact mistake that caused the OOM incident. The article uses begin/commit with optimistic locking, but doesn't mention that the default isolation level, e.g., read committed in PostgreSQL, can cause phantom reads in the reconciler. For wallet systems, use repeatable read or serializable to prevent the reconciler from seeing inconsistent snapshots of pending transactions. The article mentions TTL on idempotency keys, but only shows a database-backed approach. Here's a concrete Redis-based implementation using setNXX for atomicity and automatic expiry. The article recommends materialized balance for performance, but omits that it introduces write amplification and can become a consistency bottleneck under heavy concurrent updates. For systems with extremely high write throughput, e.g., 10K writes second per account, consider using a separate balance cache, Redis, with periodic ledger replay for reconciliation, accepting eventual consistency. To debug duplicate transactions, check the unique constraint. For negative balances, verify optimistic locking. For stuck pending transactions, ensure the reconciler is running and the index exists. Use explain to check for full table scans. Let's run through some common interview questions. How to handle concurrent withdrawals? Use optimistic locking with version column. When to use materialized balance? When reads vastly outnumber writes. What happens on database failover? Reconciler picks up pending transactions. Idempotency prevents duplicates. And a few frequently asked questions. How to prevent double spend? Use idempotency keys and optimistic locking. What's the difference between ledger and balance? Ledger is append-only log. Balance is derived sum or materialized column. How to survive database failover? Ensure idempotent transactions and use a reconciler. To recap, always append to the ledger before updating the balance. Idempotency keys with a unique constraint are non-negotiable for safe retries. Optimistic locking beats pessimistic locking for high concurrency systems. And no system is perfect, use a reconciler for stuck transactions. Ready to go deeper? Up next, design a stock exchange, then design a code deployment system, then design a distributed cache. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.